Hey, what's up, SUPA kids? Another wonderful day of SUPA notes. Okay, so we're going to finish up chapter 4 today. Really, the only thing I think we have left is redox and some reactivity stuff for this unit. And then we'll get into chapter 5. So redox, this is really just a nice little review of stuff that you did in your last chemistry class. Not too much new. Now, we do a whole redox unit next semester. So again, this is just kind of some general stuff. So because of the law of conservation in a chemical equation, mass, energy, and charge must be conserved. And redox is really dealing with this charge. So if we look at, let's just look at, I don't know, how about magnesium oxide? Okay, so this is an ionic compound, and electrons are going to be transferred from the metal to the nonmetal. So magnesium has 2. Oxygen has 6. Right? And the magnesium is going to lose 1 electron there, and it's going to lose 1 electron here. And we end up with Mg plus 2. And it's an ion, so it goes in brackets. And O minus 2. But if we look at this, our Mg loses electrons, and our oxygen is gaining electrons. Well, this is how oxidation reduction is defined. So you might remember this. Leo goes grrr. It's just a little mnemonic we use to help us remember. So Leo stands for loss of electrons is oxidation. The thing that gains electrons goes through reduction. So a gain of electrons is reduction. A loss of electrons is oxidation. So when we look at this, magnesium is losing electrons. So that means the magnesium is going through oxidation. The oxygen is gaining electrons. So that means it's going through reduction. Now there's one other thing that goes with this, and it's kind of funky. So you need to remember that oxidation cannot occur without reduction. You must have both. Okay, if something's going to lose electrons, that means something else has to gain them. All right, so the thing that goes through oxidation is going to cause something else to go through reduction. The thing that goes through reduction and gains electrons is going to cause something else to go through oxidation. That's why the thing that goes through oxidation is called the reducing agent. And the thing that goes through reduction is called the oxidizing agent. Right, so up here, magnesium is going through oxidation. It's losing electrons. It's causing oxygen to be reduced. Okay, so this is the reducing agent. Oops, redo. In this case, oxygen is gaining electrons, which means it's going through reduction. It's gaining the electrons from the magnesium, which is why it's called the oxidizing agent. So hopefully most of this is review. So how do we identify if a redox reaction is, how do we identify if a reaction is a redox reaction? Because not all of them are. Well, the first thing you're going to do is you're going to have to assign oxidation numbers. Using the rules we learned in naming ionics. So, for example, all of group 1, if they're in a compound, are +1. All of group 2 are +2. An uncombined element all by itself is 0. Oxygen is -2. There are a couple exceptions. The halogens are usually -1. All of those rules that we go through. So the first thing you need to do is assign your oxidation numbers. Then you're going to compare the oxidation numbers of the reactants and products. If they change, it is a redox reaction. All right, let's try it. Say we have MnO2 plus 4HCl going to MnCl2 plus Cl2 plus 2H2O. Let's say we have this equation. I want to know, is it a redox reaction? Well, the first thing we're going to do is we're going to assign our oxidation numbers. So manganese doesn't have an oxidation number. Oxygen does. It's -2. Okay, this has to be equal to 0, so this is +4. H is +1, chlorine is -1. We don't know manganese. Chlorine is -1, so that makes manganese +2. Chlorine is an element all by itself, so it's 0. Hydrogen is +1, and oxygen is -2. All right, so that's the first thing you do. And then you're just going to compare your reactants and your products. Men is changing, and Cl is changing. Now, you're only going to get 2 changes. You're only going to get 2 elements changing. If you get more than 2 elements changing, okay, changing their oxidation numbers, okay, you assigned your oxidation numbers wrong. You're either going to get 2 or 0 elements changing. Those are your 2 possibilities. All right, so I have 2. I have 2. So now let's just kind of bring this down. We got Mn plus 4, and it's turning into Mn plus 2. And I have Cl minus 1 turning into Cl2 0. Now, to go from +4 to +2, it needs to gain electrons. If it gains electrons, it's GR, so it's reduction. That means this better be oxidation. Well, the chlorine is going from -1 to 0. Okay, the charge is increasing, so it's losing electrons, which means it's oxidation, which is good. Now, which species is the reducing agent? Now, when I say which species, you have to be specific. Which one of these up here is going through oxidation? Well, this guy right here is the one that's losing electrons. So this species would be the reducing agent. Okay, the Cl-1 is the one that's going to lose electrons. All right, which species is the oxidizing agent? Well, it's the one that actually goes through oxidation. So the Mn+4 would be the oxidizing agent. Right? Now, this was the kind of the beginning of half reactions in redox, if you remember half reactions. Okay, we're not going to deal with those yet. We'll deal with half reactions later on, all right? So just for now, you just need to know, is it redox or not? So let's try a couple others just for fun. I want you to try these two. HCl plus KOH goes to KCl plus H2O. I want you to try that one, and I want you to try this one. Zn plus 2HCl goes to ZnCl2 plus H2. So what I want you to do with each of these is I want you to quickly tell me if it's redox or not. If it is redox, tell me which one's going through oxidation and which one's going through reduction. And I also want you to tell me the oxidizing agent and the reducing agent. So go ahead, pause the video, do the problems, then come back and I'll go through them. Okay, so hopefully you took the time and you actually did this. All right, so the first thing we're going to do here is we're going to assign our oxidation numbers. Let's do the A first. So this is +1, -1, +1, +1, -2, +1, -1, +1, -2. All right, so now we compare both sides. Both of these hydrogens on this side are +1. Hydrogen on this side is +1, so there's no change there. Chlorine is -1. Chlorine is -1. K is +1. K is +1. Oxygen's -2. Oxygen -2. There are no changes, which tells us that it is not. Ooh, this pen's dying. It is not redox. What type of reaction is this, just for fun? Well, we have an acid and a base. Okay, so this is neutralization. You could also say that it's double replacement or a metathesis reaction. Okay. All right, so let's look at the second one. All right. Zinc is an element by itself. It's 0. H is +1. Chlorine is -1. Over here, we don't have a rule for zinc, but we know chlorine is -1, so this is +2. Hydrogen is by itself, so it's 0. All right, now let's compare. Well, we have zinc going from 0 to +2, and we have hydrogen going from +1 to 0. So we have Zn0 turning into Zn+2, and we have H+1 turning into H20. Well, 0 to +2, that's losing electrons, which is oxidation. +1 to 0 is a gain of electrons, which means it's reduction. So the H+1 is our oxidizing agent, and our Zn0 is our reducing agent. Okay. So now you can kind of recognize what's going on here with these oxidation and reduction reactions. So let's talk about the activity of metals. we have something called an activity series. And it is a list of metals in order of their strength. Oops. To cause oxidation or reduction. Oh my God, I'm having trouble here today. So I have one here. This is an example of an activity series. And they're listed in, this one's in, listed by oxidation. Okay. So remember, it's loss of electrons. So, okay, this tells us which ones want to lose electrons and which one doesn't. All right, so this is going to cause, this wants to go through oxidation on the top, right? It wants to lose electrons the most. Okay, down here, this is saying really it doesn't want to lose electrons. It wants to lose electrons the least, so it's not gonna go through oxidation. Matter of fact, down here, it's probably gonna go through reduction, right? But these down here are the least active. These up here are the most active. They're the ones that want to lose the electrons. So we have some very active metals. So lithium, sodium, potassium, rubidium, cesium, calcium, strontium, and barium. These are our very active metals. Okay. And if you look right here. Okay. They're listed right up at the top. Okay, and they're not all on here, but okay, this isn't a complete activity series. It's just one that was, I think it's in the book. Okay. But these are our most active ones, or our very active ones. So all of these metals are so active that they're going to all react with water to form hydrogen gas. Okay. So all we need is some water. So if I take some lithium and I put it in water, these two react. Okay, so this is a solid, this is a liquid. Okay, they react, it's going to produce hydrogen gas. It's actually single replacement. So it's going to produce H2 gas. Right? And we'll also get LiOH aqueous. All of these guys are so reactive that this happens. Now, we have just what are called active metals also. Manganese, zinc, lead, nickel, aluminum, titanium, chromium, iron, cadmium, tin, cobalt. These are considered the active metals. Now, these metals don't react with water. Okay? They won't react with water, but they react with acids to form hydrogen gas, but will not react with water. So if we take magnesium solid and react it with, let's just use hydrochloric acid, these will react to produce H2 gas and MgCl2 aqueous. Exactly. This is what we did in the lab, okay, or what you're going to do in the lab, right? So it produces that hydrogen gas. But if I put magnesium in water, no reaction would happen. Now, if you remember back to your chemistry class, we said this. Anything above hydrogen would react with an acid. So this is kind of like our dividing line between our active elements or active metals and our inactive metals. So everything below here is very unreactive. Right, so everything above hydrogen will react with an acid, things below won't. So let's talk about our inactive metals. So we got silver, gold, copper, platinum, and mercury. So these are very unreactive elements. They will not react with acids or water. So they're very unreactive. Okay, they're not going to react with anything. Now, I do want to quickly talk about the nonmetals. Generally, we don't talk a lot about with nonmetals in redox reactions, but they do play a role. So let's talk about their activity a little bit. And the only ones I want to talk about are F2, Cl2, Br2, and I2. Okay, so actually all of these are the most active of the nonmetals. So these are the ones that you kind of have to deal with. All right, so these are in order. Okay, this is the most active. Fluorine is the most. Iodine is the least. So this is the strongest oxidizer. Okay, so fluorine wants to gain electrons. Okay, it wants electrons like crazy. So does iodine, but fluorine wants them the most. And eventually we'll talk about why. All right, so these guys up here, this one's going to go through reduction. So it's a very strong oxidizer. Right down here, this would be the weakest oxidizer. So this just gives you the trend really in group 17. All right, but those are the only ones that you'll really see in redox at all. Most of the time we're talking about the activity of metals. So let's kind of finish up redox here. And I just want to kind of give you some common redox equations. Single replacement is almost always redox. Sometimes you'll see this as a displacement reaction. I've never used that term. So our very active metals will replace hydrogen in water and acid to produce our H2 gas. This happens automatically, and it's a redox reaction. So, I don't know. So you have Na, which is a very active metal, nitric acid, HNO3. The sodium is going to replace this hydrogen to produce hydrogen gas, and NaNO3, aqueous gas, aqueous solid. Our active metals will replace hydrogen in acids. So zinc is an active metal. React it with HCl. Okay. It will replace the hydrogen. Okay, so this is also a redox reaction. So that's our single replacements. Now there are others. Over here. A more active metal will replace a metal ion in a compound that is less active. Okay, so this is what I mean by this. Okay, so I focus on, so I have a metal, and this is a metal ion, because it's an ionic compound. All right, so this would be +1. If the metal is more active than the metal ion, the reaction happens. Well, we know that K is actually very, very active metal. Okay. Ag, so it's very non-reactive. So the metal is more active than the metal ion, so this reaction is going to occur. But we could look on here too, if you didn't know that. So here's potassium. Okay, so there's my metal atom. It's well above my metal ion. So the potassium is going to replace that metal ion. And we will get KNO3, aqueous. This would be solid. This would be aqueous plus Ag solid. And this would precipitate. We could actually recover the silver. So then in this case, my metal atom is more active than my metal ion. So the reaction happens. Now, the reverse reaction can't happen. So if I put Ag with KNO3, would that reaction happen? Well, now this is my metal atom. K is my metal ion. Remember, the atom has to be more active than the ion. right? So in that case, it's the reverse. So now the silver is less active than it, so this is not going to happen. Okay, because this is more active. All right, so why don't you try one? I'll give you this. I want you to tell me, will this redox reaction happen? So if I have Al plus Rb2CrO4, will that redox reaction happen? So the question is Al more active than Rb? Because the atom has to be more active than the ion. Well, if you don't remember, we can look here. Here's my metal, rubidium. Oh, it's not on this list, right? But we listed it. Okay, so this is a very active metal. Not so much as aluminum. All right, so this is more active than the aluminum. Rb is more reactive, or more active, either one, than Al. So this will not react. This redox reaction won't happen. All right, I think I'm going to stop there. That really finishes up chapter 4. All right, so we have one more chapter before the unit test, and that's some thermodynamic stuff, which is a pretty big unit. I give you a bunch of work to do, working through chapter 4. All right, make sure you work through these questions. All right, and we will see you in class. Have an excellent day.